Okay, so good morning. Welcome to lesson 2. Today we're going to be focused on osmosis. We are going to be working out of the purple book at roughly page 120, so you're either a couple of pages in front of me or behind me. And we have this key question today. And in questions that the SEC write, they will talk about situations where inside a cell is more concentrated. And that means a particular thing, but you need to be able to put that sentence into the context of how much water is present. So let's get started. So the last day we looked at diffusion, and when we talked about diffusion, we said it was the spreading out of particles, moving from an area of high concentration to an area of low concentration along a concentration gradient. Well, osmosis is a special type of diffusion, and just like diffusion, it doesn't require energy. So in your head now you should be thinking, is this active transport or is it passive transport? And hopefully you've said that it's passive transport. So if the concentration gradient is there, so that there's high concentration in one place inside a cell and that there's low concentration somewhere else, then it's going to, osmosis will happen or diffusion happens because there's nothing to stop it. It always wants to move from high concentration to low concentration. We have to do a little bit of junior cert revision now. So we had the words in junior cert of solute, solvent and solution. And if you can use the scenario of salty water, so using that, what would a solute be? So I'm hoping that you're saying that the solute is the thing that's been dissolved, so the salt in the salty water. In the salty water scenario, the solvent, well, that's the liquid that the substance is dissolved in. And finally, the solution is the mixture of the solute and the solvent, so it is the salty water together. So pause if you need to and move on. So there's all these jokes. Why doesn't osmosis work like this? And this is you guys when you're getting to your summer exams where all of the information is in the books, there's nothing in your head and things move from high to low, so maybe by just touching the books all the information will go in, if only. So yesterday I asked you to try this little experiment where we had the 3 jellies or 3 raisins or 3 something, and we put one of them into just water and we made a salt solution, either loads of salt or very little salt, and left it for an hour and then came back and observed what happened. So we now have to talk about hopefully the results that you've seen. So after, if it didn't go into anything, it should be exactly the same as it was before. There should be no change in its appearance. It should have the same mass if you were to weigh it, but it would also look the same. When you put it into water, then you should have found that it actually increased in size. And you now need to think about what had happened for that jelly to increase in size. And the reality is that the water that was in your glass jar actually would have moved into your jelly and make it bigger. So water in this instance moved from a high concentration outside the jelly into what is a low concentration of water inside the jelly. And in terms of the salty water one, well, it depended very much on what type of concentration you made. Did you have just a little bit of salty water in there, or did you have a huge amount of salty water in there? And if you had a little bit of salty water in there, then it might have gotten a little bit bigger compared to originally. So there might have been a small increase in size. But if you put it into ridiculously salty water, you may have seen that it actually got smaller. So in that scenario, what happened to our original jelly? Well, actually the water that was in it must have left. And that's why it might have shrunk in size. This one you don't always see with jellies and raisins, but you should definitely see the result for this comparison. So now we're going to look at the theory behind those observations. So you have this picture on page 120, and what this is like, this is our jelly, and this is our glass of water. So in the scenario where we put it in, the water will move through the barrier. And if we could set this off, the numbers would change. The number here would increase and the number here would decrease, and this would stay the same because the glucose can't fit through the membrane. I'm going to skip forward slightly onto page 121, and you have this piece writing up here. So we have scenarios whereby they will give you a cell and they'll tell you it is going to be more concentrated than its surroundings, or the surroundings were more concentrated. So they're talking in that sense about the salt and water rather than the water. So it says up here, it's very unlikely that the question will reference water concentration inside or outside directly. They always hide it, and you have to understand what's the hidden bit. So here in this part of your diagram, this is a high concentration of water on this side. Once you put anything into water like salt and sugar, straight away that is going to be a low concentration of water. So that's on this side. And in the question, the way they refer to it is they talk about something being more concentrated. And if it's more concentrated, it means that there is glucose or salt or sugar or something else present. So more concentrated in the questions is referring to the salt or the sugar that you are putting in there. So straight away, the thing that I really want for you to get is more concentrated. It talks about it's more concentrated in salt or sugar, and it means low water. And water is always going to move easily from high to low, so that is how you know then that the water moves in, and in the case of our jellies, that they got bigger. You also have 3 little circles on page 121. So just below the blurb, more concentrated will always mean less water. That's really, really important. And in your 3 little circles, I'd like you to draw something that's like this. And we're going to look at it in terms of more concentrated up here. Apologies, I can't fit it in. Means less water concentration. Going all the way to here, so this middle diagram will be in the middle. But down here you will have, this is going to be a very high water concentration. And down here it is going to be less concentrated. Okay, so the more concentrated always refers to salt and sugar, how much of that is in there, whereas you need to translate that into water being present. So less concentrated means, again, we're talking about salt and sugar when we talk about less concentrated or more concentrated. So now we're going to flip back to page 120 and just give yourself your SEC definition for osmosis. You can do it in 3 sentences. So sentence 1 now, osmosis is specifically the movement of water, so that's why this is in caps. It is across a semi-permeable membrane. So that is sentence number 1. And water will move from a region of high concentration to a region of low concentration. That is sentence number 2. And sentence number 3, if you can remember it, great. It's along a concentration gradient. Now you also have this picture here, and this is giving an example of an artificial semi-permeable membrane. So usually semi-permeable membrane is our cell membrane in biological systems, but you can also have artificial cell membranes. So this is an artificial cell membrane. It is semi-permeable, so it lets some things in like the water, but it won't let other things in. Okay, so when we do our practical, you'll see this word and you need to know this word. It's called visking tubing. So we have water here, and on this side we have high water concentration. So this is our glucose on this side, so straight away this gets the label more concentrated, because there's more sugar on this left hand side than there is on the right hand side. And if it's more concentrated, then straight away you can confidently say that there is less water on this side of your semi-permeable membrane. Now, we will do this practical when we're all back together again, but in the interim, you are going to do it remotely. So you need to pause your video, and there is a QR code on page 121 that has the blurb for the Leaving Cert practical in there. You will see on the bottom of page 121 there is a table of data, and if you watch that video you should be able to fill that data in. So I'd like you to pause now, have a look at that QR code. If you can't, have no way of looking at a QR code, then in Google or whatever browser you use, you go into YouTube and you search for biology bugbears osmosis experiment, and it will come up. So go and do that now. Have a look at the questions. So you're filling in your table of your data, and you're having a look at the questions on the top of page 122, and then come back to this video. Alrighty, so you should have had a look at the video by now, and the data that you should have collected should have been 15.9 before, 20.8 before, 15.9 before, and 21.8 before. Your appearance, you would have roughly started with your visking tubing half filled, and after this should be still half filled, so there should be no change. But here we use the word increase in turgidity. So essentially what that means is the little bag of visking tubing is now full of water. It's really, really thick and solid, not at all squishy as it would have been beforehand. So I'm just going to take a little step back here. You need two diagrams to explain this experiment. So you always do your kind of test and your control. So you will have beakers, and the beakers will both be filled with water in both. And when we come back to lesson, you will get this little piece of tubing. You tie a knot in one end and you fill it with water for our control. So this is going to be our control side. So we fill this with water in here, and this is called visking tubing, and this is your semi-permeable membrane. Visking tubing, and it is your membrane. And over here we do the exact same thing in that we get the visking tubing again and we fill it up, except this time we fill it with sucrose or glucose or salt, doesn't matter. So again, this is your visking tubing, and this is acting as your semi-permeable membrane in an artificial scenario. Okay, so please make sure you have those diagrams at the top of page 121. And if you want for yourself, so here the mass before and after doesn't change in our control. And what that means is that there's water moving in, but it's also moving out at the exact same rate. There's no change. Whereas in your test sample with your sugar solution or your salt solution or whatever it is, so again we just go back. This is high water. This is low water. And it's more concentrated in here in terms of salt or sugar or whatever we're putting in, and the water will come into this, and this is the reason why this gets bigger, because there's a higher concentration of water outside. Now you have all of these questions that hopefully you've had a look at, and we just going to go through them now to make sure you are good with them. So the equipment that we need for this particular experiment is our distilled water, our sucrose solution, our whisking tubing, and our beakers. Which piece of equipment acts like your semi-permeable membrane? So that is your whisking tubing. The control is whisking tubing filled with the distilled water and put into distilled water. So there should be no change in your control if you've done this experiment right. The test sample for this experiment is the whisking tubing filled with sucrose, and you put that into your beaker of distilled water. The readings and measurements that we took is you record the turgidity of your whisking tubing, so it's half filled is one observation, and another is the mass. And again, I can't reiterate how important this word is. So the mass, obviously you're using your balance, and then afterwards we compare both the turgidity and the mass of each, and the results show. So the whisking tubing filled with sucrose was more turgid and had an increase in mass, whereas the whisking tube filled with distilled water showed no change. Now there is no question for this, but what's the explanation behind it? So in the test sample, water moved into your whisking tubing by osmosis. So please make sure you put that in there and that you are happy with it. So in your control, there was no difference in water concentration. Inside and outside the tubing. So there was no change in mass or turgidity. Alrighty, so that's us. There will be homework in your class notebook. So there's a class notebook page for your homework, and there's also going to be the notes section where you're going to put photos of what you've filled in today. Okay, talk to you soon. Bye bye.